Namaste and welcome to this lecture on mathematical foundations for machine learning. In the last couple of weeks we saw ideas of linear algebra, and in the last week lecture we looked at the basic ideas of probability, where we looked at a random experiment, we looked at the sample space associated with the random experiment, the events that you can have, which are basically the subsets of our interest from the sample space, and then we said that that is what we are going to map to a number between 0 and 1, which we called as the probability. And then we looked at different kinds of events, and then we said okay, there could be mutually exclusive events where occurrence of one gives a complete update about the non occurrence of the other, and then we looked at independent events where occurrence of one event not giving any insight into the occurrence or non occurrence of the other, and then we looked at conditional probability where we could gain a partial update about event A upon the occurrence of event B, and then we looked at total law of probability. Then we said that okay, we look at Bayes' theorem where when you have multiple causes that could result in a particular effect. Now we wanted to know, given the effect has happened, what is the probability that this was what is the probability of this particular cause being responsible for that effect, given that the effect has happened. So that is where we saw Bayes' theorem and so on. Now what we are going to do is we are going to move a bit into much more deeper ideas, where we will be talking about the notion of random variables. We look at the notion of random variables now from now on, and we will be studying about probability distribution. We look at probability mass functions and probability density functions. These are things which you might have already read, but then we will just try to get more insights on this, and this will help us to relate to whatever that we do in our machine learning. Say for example, it could be something like okay, given that I have this particular feature, what is the probability that it belongs to this class, and so on. You could have distributions and so on. So for that what we need is we need to know the idea of random variables, we need to know some of the interesting things related to random variables and so on. So this entire week lecture is basically devoted to the idea of random variables. We look at single random variables, multiple random variables and so on, and we will also look at the idea of expected values and a whole lot of things. Okay, great. So let us get on to the notion of random variables. What are these random variables? Because typically when you are taught a probability course after Bayes' theorem, people immediately start talking about random variables. So we must know, like, what is it to say a random variable? Why do we even need this idea of random variables? If we get to understand this, then it becomes easier for us to get much more insights. So let us look at the notion of random variables. So what is a random variable? Why do we need this? So let us go back a bit behind and then see, like, what are we trying to do, right? So the first thing is, like, there is this name which says random, and therefore let us see if we can associate this to let us say a random experiment, right. We could see if that happens. Okay, so let us look at random experiment. So first of all we have this notion of random experiment. So this random experiment is basically associated with a sample space, let us say omega, and let omega 1, omega 2, etc. this be the elements of omega 1, omega 2, omega etc., omega n etc. be the what would you call the elements of the sample space, basically the outcomes, right, be the outcomes of the random experiment. Okay. Now, what is the connection between the sample space associated with a random experiment to the random variable? So, this is not something which we do not know. It dates back, in fact, if you can look at the stories of Mahabharata, from there you can actually draw some kind of association with this. For example, the game of dice was played, right. When the game of die was played, the game did not stop with just rolling some number and saying, okay, declaring one of the teams to be the winner. The game had much more what would you call, much more than what it meets the eye. The game was not just roll a number and get declared as the winner, but then for every number that was rolled you had a reward to be associated. I am quite sure people who have heard about the story of Mahabharata, you probably know it. Like when this first number was rolled, okay, one of the two sides said that, okay, if I roll this number, then your army is mine. If I roll this number, your kingdom is mine. If I roll this number, your brothers are mine, and so on. That means for every number there was a reward associated with that particular outcome. So basically the die game that people played was a random experiment. You are trying to roll the die and then look at the outcome of that particular experiment for that particular trial, and if that trial comes out with the number that I call out, I associate a reward with it. It could be reward in one case and it could be a penalty in the other case. So, it is anyway it is going to be some kind of a reward. So, what are we trying to do here? Whenever we have a random experiment, I want to associate a reward with every outcome of the random experiment. I want to do that because I mean ultimately I can figure out, like I would be interested in figuring out what is the chance of me winning this many games, let us say in a tournament of, let us say 5 games. What are my chances of winning? I am quite sure most of us would have seen this in your mobile apps, where one of the most famous mobile app that you use for online purchase would have the spin wheel contest, right. It would have the spin wheel contest where it would say, okay, fine, it could be let us say a smartphone, then let us say it could be a tablet, then it could be a what do you call, it could be the slim PC that you have, then let us say you have this AirPods or EarPods, whatever that is, then there is a smart watch, and then you see that there is, okay, there is always this which comes into picture, like 100 rupees cashback, then you have 50 rupees cashback, and of course the most important stuff, which is better luck next time. This is something which you would see, and remember, whether we get a prize or not, we are tempted to do this because the rewards are tempting us to do it, right. Suppose if I had just told you, look, I have the spin wheel where it is just this, let us say I have S1, S2, S3, S4, S5, S7 and S8. I tell you, spin this wheel, and wherever it comes to a halt, the position shown by the arrow there, that is going to be the outcome of the experiment. I am quite sure many of us will not even touch this. The question that we will ask is, what is the point in spinning this wheel, because there is nothing great about spinning this wheel. Let us say this is wheel 1 and let us say this is wheel 2. Okay. Now what I am going to tell you is, look, okay, wheel 1 was not interesting because, okay, it is just spinning the wheel and then leaving it out. I tell you, look, I am going to put these rewards with each of those outcomes. See, when you spin the wheel, the position that the arrow shows when the wheel comes to halt is basically the outcome of this random experiment. Now what I do is, I just take these stickers which say smartphone, tablet, slim PC and all those things, and then I am going to put it over W1, that means the wheel 1, and I am going to ask you to rotate this or spin the wheel. Now we are more excited to spin the wheel because we know that if we spin the wheel and based on our luck or whatever, wherever the wheel halts and wherever that position of the arrow that you have, you are going to get that as your reward, right. You are going to get that as a reward. So, the question is, I would not be interested in figuring out what is the probability of getting S2. My question will now change, what is the probability of me winning a tablet, which means I am going to associate the probability that a probability of getting S2 with the probability of winning a tablet. That means I am going to map S2 to something, right. Here of course I am going to map it to the reward, but then we will see that this mapping basically happens from the sample space to the real numbers, right. And it is for this purpose that we actually use random variables. What is the purpose? We typically say that, look, I want to associate rewards with every outcome of the random experiment. Is that for that purpose we use a random variable. So, let us write this a random variable is used for associating is used for associating a reward with every outcome of a random experiment. Okay. It is used for associating a reward with every outcome of an random experiment. Now, how do we do this? That is the question, right. How do we do this? For example, just take a 5 match series in cricket game, in the game of cricket. It could be, let us say, one day test or T20 or whatever it is. Let us say you have 5 match series. Now, every game, the outcome of every game is just going to be team A winning or team A losing, right. Of course, you have this tie no result, forget about that for the time being. We are going to say that, look, either team A wins or team A does not win, team A loses. Now, if I want to look at which team has won the maximum number of games in the series, what do? We count the number of wins for each of these teams, right, for both the teams. Therefore, what I do is I associate a 1 with the win and a 0 with a loss. Now, if I say that team A has won the series, that means I count the number of ones there. If the number of ones is for team A is more than the number of ones of team B, then you say this team A has won the series. That means my win or loss is going to be the outcome of the random experiment called that one particular game or one match. That win or loss is now encoded as 1 or 0, and now I am going to ask you this question, what is the probability of team A winning 3 games in a 5 match series? You have that, right. So, this is basically what the purpose of a random variable is. A random variable is used for associating a reward with every outcome of an experiment. So, what does it basically do? How does it associate this reward? So, what do we do? Let us look at this. So, I have my sample space. Let us say I have my sample space, this is my sample space. Let us say which has outcomes omega 1, omega 2, etc., omega n. For the time being, let me keep it finite. So, this is the sample space omega, I have this. Now, what does the random variable basically do? The random variable is going to map each of these outcomes to a real number. Let us see what it is. So, it takes omega 1 and then maps it to something, takes to omega 2, maps it to some real number, maps omega n to some real number. So, what I would say is the random variable x maps omega 1 to let us say x 1, which is a real number. X of omega 2, it maps it to another real number, let us say x 2, and so on. X of omega n, it maps it to another real number, let us say x n. Right? Where have we seen this? This is something very interesting. Best example, just look at the case of the toss that happens before a cricket match. Now, what do? Basically, one of the captains is going to throw toss the coin, the other fellow is going to call out what is the face that is going to come up. He is going to say that, look, okay, it is going to be head or tail. Suppose there are two teams, let us say A and B. I have two teams A and B, and the toss is being done by captain B. So, captain A is going to call out what is going to be the toss outcome. Now, what we say is captain A wins the toss if what happens, if the face that he calls out comes up, right. So, suppose I take a coin toss experiment where my omega is equal to the set contains head tail. So, these are basically the two outcomes of the coin toss experiment that we have. Now, what happens is if A calls out head, and it turns out to be head, the coin toss results in a head, I would give this a number 1, saying that whenever you get a head, I will associate head with the number 1. Whenever we get a tail, I will associate with the number 0, which means now what I am going to do is I am going to say that, look, I have a random variable x which is going to look head to be the success. So, I will take x of h is equal to 1, and I will say x of tail is equal to 0. That means, whenever you have a head, it is going to output a number, it is going to map it to the real number 1, and whenever you have a tail, the random variable x is going to map it to 0. So, how is it going to be? I have my head and tail, the coin tossing experiment, I have this. Now, what does x do? X takes tail and then marks it to 0, and x takes head and then marks it to 1, maps it to 1. You could have another random variable which says like y, which is going to map tail to 1 and head to 0, that is still allowed. So, what we do is it depends on what is it that you want, what is it that you are looking at the end of the random from the random experiment, right. So, a random variable associates a reward with every outcome of the random experiment. Now, what is interesting in this case, if you see, it also maps the outcome of the random experiment to real numbers. Now, in this case, let us say in case of a cricket match, the toss that happens before the cricket match, the question is, okay, fine, big deal, I have mapped head to 1 and call it success, and tail to be 0, call it a failure. Now, what is the reward that is associated with it? That is a good interesting question. See, suppose I call a head and then I get a head there, that means I have won the toss. The reward is basically the toss winning captain gets his gets to call what he wants to do, whether he wants to bowl first or bat first. So, that is the reward that you have, is that clear? So, let us write a formal definition of a random variable. A random variable is nothing but a random variable x. A random variable x maps the outcome space of a random experiment to set of real numbers. Okay, so what does it do? For every omega, which is basically the outcome from the sample space, for every omega and omega, the random variable x maps x does the following: x of omega in omega is basically a, I would say it is basically okay. So, x is such that it is basically a map from omega to r, it is a map from omega to r. Now, let us take some examples and see if we can understand this better. So, the first example that I am going to do is this example 1. I am going to consider tossing a coin once and counting the number of heads and counting the number of heads in a single trial anyway. I have said that you are going to toss a coin and then what you do is you just count the number of heads in the single toss, right. So, x is going to count, x is the random variable which counts the number of heads in a single trial of a coin tossing experiment. Right, it is going to count the number of heads in a single trial of the coin tossing experiment. So, what are the values that x can take? So, what is the, let us see from the beginning. So, what do we have? We have the sample space omega to be equal to tail comma head, right. Now, what does the random variable do? You are tossing the coin one time. So, I am going to take x of t is an element of the sample space. So, x of t, it is going to associate a number 0 because that corresponds to 0 head, and it is going to take head and then it is going to associate a number 1 because that corresponds to 1 head, right. So, what are the values that the random variable x can take? This you can simply say x is equal to 0, x is equal to 1, provided you tell very clearly that x counts the number of heads. Here I am going to say x counts number of heads in a single trial, in a single toss. Then I do not have to do this x of t is equal to 0, x of h is equal to 1. When I say x equal to 0, it is understood that I have got a tail, and when f x is equal to 1, I would say that the toss is resulted in a head. Is that okay? So, this is something which is very easy to understand. So, in the sense, suppose I say that it counts the number of heads, then this is what it is. Let us take a second example. Let us take a second example where I am going to toss a coin let us say 3 times, toss a coin 3 times and x counts, the random variable basically counts the number of tails in 3 tosses, right. It is going to count the number of tails in 3 tosses. So, first of all let us write what is the sample space here. The sample space basically is a triple that you have. How do we get the sample space here? The sample space is basically the Cartesian product of the toss 1 with toss 2 with toss 3. So, what I am going to do, I am just going to represent here. So, I am going to have toss 1, I am going to have toss 2, and let me say I have toss 3, right. Now, my toss 1 can be a head or it can be a tail, right. My toss 2 again can be a head the toss 1 being head, the toss 2 can be a head, or toss 1 being head, toss 2 can be a tail. Similarly, I have this is head and this is going to be tail, right. And for every for the every outcome that you get in toss 1, toss 2 has, you have this two possible outcomes which are basically head and tail, but corresponds to head I have in the toss 1 I have head or tail, corresponding to toss 1 tail I have toss 2 to be a head or tail. And now what I am going to do is I am going to look at toss 3. For every combination here I have a head or this is a tail. Similarly, I have this which is a head or a tail. Then the same thing, I have a head here, then this is a tail, then I have head and tail here. That means, my sample space, if you see, it is going to be head head head, head head tail, head tail head, head tail tail, tail head head, tail head tail, tail tail head and tail tail tail. So, the sample space is going to be the following. So, the sample space omega I am going to have is basically this. It starts with head head head, then I have head head tail, then I have head tail head, head tail tail, then I have tail head head. Let me do this, tail head head, then I have tail head tail, tail head tail, and then I have tail tail head, tail tail head, and then I have tail tail tail. This is what I have. So, what I will do is let me put this guy also here. Right, we have this. Now, what is the random variable supposed to do? It counts the number of tails in 3 tosses. It counts the number of tails in 3 tosses. That means, the random variable is going to do something interesting here. It is going to take this combination H H H and it is going to code it as 0 heads, 0 tail. That means, you do not see a head in all the 3 tosses. Similarly, it is going to take this x of head head tail or tail head head or head tail head. This is going to give me number 1 because I see only one tail in 3 tosses. Then I have head tail head or tail head tail or tail tail head, that is going to get coded as 2, and then I am going to have x of tail tail tail, which is going to be 3. So, this is very clear because when I toss a coin 3 times, these are the only possible number of heads that I can get. Either I get 0 heads, which corresponds to all 3 tosses resulting in head, 0 tails which corresponding to all 3 tosses resulting in head, or one of the 3 tosses results in a tail, the other 2 results in head, or 2 of those 3 tosses resulting in tail and the third one giving you a head, or all the 3 tosses being tail. So, this is precisely what the mapping is. So, let us look at how this the mapping, how does the mapping happen. So, I have this, I have let us say head head head, and then I have this event here. I am going to have head tail head, tail head tail, tail head head, and then head, head, tail. Then I am going to have this, which is going to be head, tail, 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 head, tail, head, tail, and then I have this one, which is going to be tail, tail, tail. Oh, this is head, head, head. So, what is the random variable going to do? The random variable is going to do something interesting here. So, what does it do? The random variable x basically maps this to the real number 0, x of h is 0, then this is going to get mapped to 1, x of this whatever we have is 1, then this gets mapped to 2, and then this gets mapped to 3. Right, that is the mapping that we are looking for. So, the question is, what do we do from here? Okay, fine, it has done the mapping, but what do we do from here? I do not ask for, I will never ask hereafter. I mean, once the mapping is done, I am not interested in the order in which the head appears or the tail appears. My interest is in finding out the chance of getting 2 heads, or chance of getting 3 heads, or chance of getting 2 tails, chance of getting 3 tails, chance of getting no tail. We have all that, right. Okay, we will come back to that in a few minutes, but let us look at some more examples to get our understanding of random variables a bit better, right. Let us take another example, example 3. Now, rolling of a fair die, let us say rolling of a 6-face die. Right. So, what is x, what is the random variable that I am going to associate here? So, I am going to say x is or y is the random variable that counts the number of dots in the face that comes up when a 6-face die is rolled. Right, it is going to count the number of dots in the face that comes, basically it is going to describe the face that comes up. Now, whenever we say that okay, what is the outcome, what are the possible outcomes that you get when you roll a die, we straight away say that look, the outcomes are 1 to 6, but typically what you see on the die is going to be the dots that you have. So, the sample space omega in this case is going to be the following. I have a face with a single dot, I have a face with 2 dots, I have a face with 3, then we have a face with 4 dots, we have a face with 5 dots, and we have a face with 6 dots. Now, what is the random variable supposed to be doing? The random variable y will take this 1 dot and then will associate a number 1. The random variable y will take 2 dots and associate it with the number 2. Y with 3 dots is going to give me 3, and y with 4 dots is going to give me 4, y with 5 dots I am going to get 5, and y with 6 dots I am going to get 6. So, now you see the random variable has mapped every outcome of the sample space of the random experiment to some real number. Okay. Let us take one more example. Let us take another example where we are going to look at okay, example 4. I give you a simple task now. What is that? Just go and stand in a traffic signal and figure out how many number of cars pass through the traffic signal, right. You could even take how many number of vehicles pass through the signal, could take how many buses or probably two wheelers or three wheelers or four wheelers or whatever, right. So, I will give you this task of observing the number of vehicles that cross, the number of cars that cross a particular traffic signal, right. Remember, this number is going to be a random number, right. So, the sample space is going to be completely the set of all cars in possible in your city or probably the country that you are residing at or the state that you are residing at. So, the thing is, I want to count the number of vehicles that pass through a particular signal. I want to count, let us say random experiment is counting the number of vehicles that cross a traffic signal. In a given interval of time. Right, I am going to look at this. So, let the random variable associated here with this experiment be, let us say x, let x be the random variable associated with this experiment. Right. So, what we do is whenever there is a vehicle that passes through the signal, that crosses the signal, it could be cycle, it could be three wheeler, it could be any vehicle. The moment one vehicle crosses the signal, you increase the count by 1. If no vehicles cross, you keep it as 0. Therefore, x can take values here, the range of x, the x can take values from 0, 1, 2 etc. infinity, right. It can take values from 0, 1 to infinity. Let us take one more example and then we will try to summarize all these things. Let us take another example, example 5. Assume that you and your friend wants to meet up for a coffee at a particular place. So, you arrive early, let us say you arrive early. Now, the question that I ask is, what is the amount of time that you need to wait, that you wait before your friend comes, right. Assume that you all plan to meet, you both plan to meet at let us say 4 p.m. at a coffee shop. So, the question that I have is, what you arrive early, the question is what is the time interval for which you will wait before your friend arrives. In that case, it becomes an interval, right, it becomes an interval. So, the time, I mean a better example is like probably assume that you have a train to catch at let us say 4 p.m. and then it is not that exactly at 4 p.m. you go to the railway station, you probably go a bit before. So, what is the time that you wait in your railway station from the time that you reach to the time the train departs, that is the time interval that you have. So, the time interval that you need to wait one has to wait let us say at a railway station from the time he or she reaches the railway station and railway station to the time the train departs. Right. Assume that you reach the station at time say t1 or at time t you are there in the station, right. Now t plus say some t amount of time you would have to wait in the station before the train departs. So, this is going to be a interval, right. This is going to be an interval, and that interval is going to be random depending on what time you reach the station. So, what I will do is I will say t1 to t1 plus t, and I would say this t is going to be the random variable associated with this experiment. So, what is it the random variable the random variable t, what is it going to do? It is going to tell you from the time you reach the station to the time the train departs, that interval is going to be random, that is a time interval which is going to be random. So, I am going to associate with that time interval a random variable t, right. Now, what is interesting is if you look at all the 5 examples that we have considered here, which is like we started off with a very simple experiment of tossing a coin once, where the and then counting the number of heads that appear in the single toss of the coin. In this experiment I associate a random variable which is basically going to count the number of heads. Therefore, the sample space was tail and head, and the random variable took only 2 values 0 and 1. And in the next case I said no, let us not stop with a single trial, let us toss the coin thrice, and we are going to count the number of tails in 3 tosses we said. So, x is going to count the number of tails in 3 tosses. Now, here x is going to be taking value 0, 1, 2, 3, that is the maximum that you can have. That means it can have no tails to it can have at the maximum 3 tails. So, that is the random variable that we have here. And then in the third example we said that look, I am going to roll a 6 face die where the random variable is going to count the number of dots in the face that comes up. So, basically you map the number of dots, you count the number of dots, and then associate a real number with that. In the case of example 4 we said that let us go stand at the traffic signal, or probably go stand in a it could even be this, let us go stand in front of a shopping mall, count the number of people who walk into the mall. We are not worried about whether they are going to purchase or not, they are just going there, just go count the number of people that walk into a mall, or in this case you count the number of vehicles that cross a traffic signal. No, of course, what are we going to do with this count? It is a different case. We may be trying to build probably construct a flyover or an underpass at that place to ensure that it could be some result, it could be the consequence could be something else, let us not worry about it. What we right now have is we just want to figure out the number of vehicles that cross the traffic signal. So, here if we see the random variable is going to take values from the set 0, 1, 2, etc. And the fifth experiment that we did was we said okay, assume that you have to catch a train, you go to the railway station at some time t. Now, what you do is look at the time interval that you are going to wait before the train departs. So, that time interval t is a random variable we have. Well, this is pretty interesting because in the first 3 examples that we took, the random variable took only a finite number of values. That means in the first experiment random variable took only values from only the set which contains only 2 values, namely 0 and 1. In the second experiment the random variable basically took values from a set containing 4 values, namely 0, 1, 2 and 3. In the third example of rolling of a die, the random variable y could take values from 1 to 6, these are all finite. And in the next example that we took, x is taking a value which is infinity. which can it can take an element, it can take it can take a value from an infinitely many number of values. But what is interesting here is this is basically a countably infinite set. You are just saying 0, 1, 2, 3, it is taking values from a countably infinite set, alright. If you look at example 5, it is basically an interval, let us say a comma b, and how many number of points are there between a and b? In the interval a and b, suppose I take this interval, let us say 3, 4, between 3, 4 I have infinitely many number of points, and let us take this 3, 4, you have infinitely many number of points. I will take a point in between these two, let us say 3 and 3.5, between 3 and 3.5 I have infinitely many number of points. Let me take 3 and 3.05, between 3 and 3.05 I have again infinitely many number of points, and so on, which means in this case we already called this as an interval. The random variable still takes values from an uncountably infinite set or continuum. Infinite set or interval, right. So that means you have a random variable which takes values from a discrete set, and you have a finite set or discrete set of numbers, and then you have in the fifth example it is going to take an interval, which means you have a continuum. So I am going to say that random variable, I am going to classify this random variables into two, and once we do this classification in the next class when we come back we will actually look at what they actually mean. So I am going to look at discrete random variables. Discrete random variables, I am going to say x is a discrete random variable if it takes values from a finite set or a countably or a countably infinite set. Okay. Example 1, 2, 3 and 4 are discrete random variables, okay. Whereas I have a continuous random variable x is a continuous random variable if it takes values. In fact, there is another way of defining it where we look at cumulative distribution function, which we will do a bit later, but for now what we will do is we will take this definition to be where with respect to the range of values that the random variable can take. So x is a continuous random variable if it takes values in an interval. Or let me put it this way, I will just define one more term here and then let me put this properly. So I have I am going to define a range of a random variable. So range of a random variable, this is nothing but the set of values that a random variable can take. So what I do is, if the range is finite set or countably infinite set, then you call that as a discrete random variable. In this case I am going to say x is a continuous random variable if its range is an interval, if its range is an interval. Right. we are going to stop. We are just going to make this definition here, where we say that okay, its range is interval, then you call it as continuous random variable. If it is finite set or countably infinite set, you call that as a discrete random variable. So, for in this lecture what we did is we were basically looking at why do we need random variables. We said that random variables are used to associate reward with the outcome of a random experiment, and then we said that a formal definition is basically a map that takes you from the sample space to the what you call to the real number set of real numbers, and then we said that okay, you have discrete random variables, you have continuous random variables, and we also saw how the mapping happens. The one question that we have not answered here is okay, I have done the mapping, what is it that I look for from here from this mapping. Number 2, we have defined discrete random variables and continuous random variables. So, how do we characterize these two guys, and that will form the crux of the next lecture. Namaste.